Nobody cares.
Michelle, could you mute your, I can mute.
Am I muted? Am I not muted? I'm just...
There you go. Okay, thank you. I think we're good to go. Now, what was I going to do? I was going to record. No, we're recording. There we go. Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for Friday, January 28, 2022. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a calm evening before a major snowstorm hits my hometown of Rockport, Massachusetts. These Earth and Space reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our life-sustaining environment, and who wonder about the greater cosmos, including our place in space and moment in time. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. They are also in regular rotation on the 1623 Studios Community Access Television Cable channel. I'm grateful for the continuing interest and support shown by members of the Rockport Research Explorers, Rockport Cultural Council, Gloucester Area Astronomy Club, sundry science colleagues, far-flung friends, family, and other curious folk. Thank you for participating. This evening, I am pleased to be hosting Alexandra Trunnell, who will talk on the quest to find habitable exoplanets. Alex is a mathematics, science, and technology teacher at Meridian Academy in Jamaica Plain, Massachusetts. Over the past 2 years there, she has founded an observational astronomy program, complete with a mobile research telescope. That is how I crossed paths with her as she was observing with her telescopic rig at Halibut Point State Park here in Rockport. Alex has a degree in physics and astronomy from Vassar College, where she worked with Vassar's 32-inch telescope for 4 years and led the observatory's research with her senior thesis on exoplanet transit timing variations. Alex's goal is to optimize the Meridian Academy Mobile Observatory, or MAMO, for exoplanetary work. In February, she will be presenting on her research and education endeavors at the Space Center in Houston as part of NASA's Space Exploration Educators Conference. So welcome, Alex. The Zoom platform is all yours.
Thank you so much, Bill. It's lovely to be here and it's wonderful to see you all. Thank you so much for coming. As Bill said, I'm going to be talking a little bit about exoplanets today, the research I did with them at Vassar and some of the ramifications and other research corresponding to life in the universe and how we can get there with current observational methods. Let me go ahead and share my screen and we'll get going. So this is Wobbly Planets and Seeing Stars, Finding Habitable Planets Through Observation. As Bill said, I'm a math, science, and tech teacher at Meridian Academy, which is an independent school down in JP. I'm based in Boston, and I think that this is a great school, and it is an incredible place that has allowed me to extend my astronomy research into my education background as well. So first, I start with a question. How many planets are there? I gave this talk to my students. I teach 2 astronomy electives, and they asked if I would give them the talk before I give it to you all, and they were great in giving me some feedback. And when I asked this question, how many planets are there? They, of course, answered with the classic 8. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. I'm sure we've all heard the classic mnemonic to remember it. My very educated mother just served us 9 pizzas, but there is no more Pluto. So I was informed that it is that she now serves us nachos. These are the planets inside our solar system. However, for someone like me, who's worked with exoplanets for a long time, I no longer view planet as a word that means 8 things. Instead, when I think planet, I think of all of the things outside of our solar system. And in this GIF, you can see just a small snapshot of those things. This is the Kepler Orrery 3, which is sort of mid-2010s, so a little outdated at this point, but I believe one of the better GIFs that's ever been produced. Here's a closer view at that. What we're looking at here is a list of just a few of the exoplanets that we have found in the last 2 decades. Really since about the turn of the 2000s, exoplanetary research has taken off dramatically, particularly with the Kepler Space Telescope and the finding of more transits. And I want you all to sort of take note of this GIF, because we will start to see that there is a very specific kind of planet that we are able to find with current methods. So you're seeing a lot of very large dots, very close to stars. And I want everyone to keep that in mind as we move through here. So the first question, of course, is how can we detect exoplanets? Most of the planets in our own solar system have been found for as long as humans have been gazing up at the sky. And even the ones that were not as anciently known have been found within the past several hundred years. So how is it that we've come to detect exoplanets so recently? Well, there are many methods. I'm going to quickly sort of do a nice roundup of them and give you an idea of how many planets we found with each. The first method I'll talk about is the least common. This is the astrometry method. And to date, we have found 2 planets, which is rounded a whopping 0.0%, considering all exoplanets we found. Astrometry relies on the wobble of a star and a planet system. So we're looking at planets that are close enough and massive enough to cause a notable wobble in their star. Now, what this means is the star appears to wobble in reference to the background stars, as you see here. So this is a notable shift in the motion of a star. It causes a very large planet with a very large gravitational influence to do this, which is part of the reason it's such a rare method and one that has yielded so few exoplanet detections. That being said, we have found 2 planets this way, so it is still one worth mentioning and still an interesting method to discuss. Next on the docket, we have the direct imaging method, one that is fairly new. And when I was putting together this presentation for tonight, I adapted a very similar presentation I've given before. And in the 3 or 4 years it's been since my last time giving this presentation, this number has gone up considerably. So this is a relatively modern method that is sort of happening more and more every day, currently accounting for 57 planets, 1.2% of our total exoplanet count. Direct imaging is pretty much exactly what it sounds like. If we look at a star, it's too bright to see anything, cover up the star, and suddenly exoplanets become visible. So yes, we have seen exoplanets for ourselves. We have directly imaged them by covering up the brighter stars. Again, we're looking at very close planets that are large enough to have a notable amount of reflected light that then pop up in our observations. Next up is gravitational microlensing, one of my favorites just because it's so darn cool. Another method that's really gotten more planets found via it over the past few years, up to 2.6% of all planets found this way, 121. Gravitational microlensing relies on the fact that gravity bends space-time. So when light is emanating from a star, it is cast out through space-time, as you see here. When something massive like a planet crosses by that light, it bends and contorts that light and actually causes it to be microlensed through gravity. So if you see our little Earth dot at the bottom, when the planet passes by, different light converges depending on where the planet is in its path. So gravitational microlensing, very cool, very exciting. But only 2.6% of planets have been found this way. Next up, we have a more common method. You might have heard of this one, the radial velocity method. Now, for a long time, radial velocity was like the method. This was really the primary way we found exoplanets. And it's only recently, really since the launch of the Kepler missions, that transits have overtaken it. A little bit of a spoiler alert there. But even with the enormous number of transits we see in recent times, the radial velocity method still accounts for almost 1,000 planets, which is about 20%. Radial velocity, similar to astrometry, relies on the fact that massive planets wobble their star a little bit and cause them to actually move. This is an effect that all planets have, but the bigger the planet, the more dramatic the effect. Now, when the star is moving to and from us, toward us and away from us, the light from the star is actually shifted. This is the Doppler effect, which you're probably familiar with because it's quite common on Earth with sound. This is what makes an approaching truck do the meow, like that noise. We see the same thing here, but with light. When it's going away from us, light is stretched and appears red shifted. When it's coming toward us, light appears purple shifted. So because of that, we're seeing the red shift and the blue shift, and we can measure that and understand the planet based off of the shifts in the star. Now, 912 planets, that is a very good number. That's nearly 1,000 planets. And we find that those planets tend to fall into a very similar category, which is Jupiter-like planets. Jupiter-sized at about Jupiter distance, 5 to 10 AU. Planets like these, right off the bat, cannot support life as we know it. Typically, these are Jupiter-like planets, which are beyond the frost line, so no liquid water, and gas giants in general aren't great candidates for life as we know it. And we'll talk a lot more about that later. So lots of planets, not great for harboring life. Which brings us to our final method, which is also our most promising for finding intelligent life outside of our own system, the transit method. And this is the one that my research is on, the one I've worked with the most. Almost 3,500 planets have been found this way, accounting for over 75% of all found exoplanets. The transit method is perhaps, I think, one of the more important parts of modern astronomy. We can get a lot out of this method, and it's really shown us an important look into the solar system, our own solar system, as well as other systems out there. So the transit method involves, as the name would suggest, a transiting exoplanet. You have a star, and we're looking at it face on, kind of like a frisbee, and we're getting a set amount of light from that star. When a planet crosses over, it blocks part of the light, and we don't see some of the light from the star as it passes us. Now, as the planet orbits, it will go behind the star. We'll see a steady amount of light until it loops all the way back around and repeats that process. Each time it passes between us and the star, we see the same amount of darkening as the transit's happening over and over. Again, this is also useful for our own solar system, and we see this effect with Mercury and Venus because they also pass between Earth and the sun. The last transit of Venus was in 2012. There won't be another one until the 2100s. I believe it's 2117. And the transits of Mercury are a bit more common. The last one was in 2016. So transiting is something we have firsthand experience with. Now, if we consider all of these methods graphed out, here is a plot of the period on the x-axis, so how long it takes them to orbit, and the mass in Jupiter masses on the y-axis, so how massive they are. Here's Earth on that scale, about a 365-day period. Here is Jupiter on that scale. So there again are the radial velocity planets I was talking about earlier, very Jupiter-like, about Jupiter distance, about Jupiter sized. We then have these sort of two other clumps of planets. We've got our clump up here on the left from transits, and we've got our other transit clump down here as well. These are what are referred to as super Earths, and these are what are referred to as hot Jupiters. We're going to talk especially about hot Jupiters because it turns out those are the most interesting planets to consider when we talk about transit timing variations. So this dark green clump is where we are headed next. So let's talk a little bit more precisely about transits. Transits have detected the greatest number of exoplanets, as we just said, and they look at a change in star brightness over time. This allows us to determine a lot of extremely useful stuff about a planet, like its radius, so the actual physical size, its semi-major axis of orbit, how far it is from its star, the inclination of its orbit, so how angled the orbit is, and its orbital period, or the length of its year. This is an incredible amount of information, and it's relatively straightforward to find it all if we know enough about the star and the actual transit itself. The more observations we make, the more sure we can be about this stuff, and the more we can start to use it to infer things about the system, even that we can't observe directly. As I said earlier, that clump of stuff that we were looking at is a clump that's known as the hot Jupiters. Hot Jupiters are large gassy planets, Jupiter-sized, Jupiter-like, but they're extraordinarily close to their star. These do not exist in our solar system. Most hot Jupiters we find orbit in several days. Mercury takes 88 days, so it's well in closer to its star than Mercury is. And all of our gas giants are out further. They're 5 to 10 AU, and it takes them tens of years to orbit, almost 100 years to orbit in some cases, not days. These definitely could not support life as we know it. They're extraordinarily hot, they're tumultuous, they're gas giants. For lots of reasons, hot Jupiters are not where we want to look when we're looking for life. So why are they so interesting to me as someone who studies the possibility of life in the universe? Well, with one planet, with one transit, the transit is periodic. As I said earlier, the planet will cross in front of the star predictably once as it orbits, right? It'll cross in front of the star, go behind, cross in front of the star, over and over like clockwork. Here's some actual data so you can see what this looks like. On the left-hand side, you can see these are 3 transits from January, October, and December, and all of them see a similar mid-time. Same with the right-hand side. The mid-time is when the planet's at the center of its transit, and the mid-time is something I want you all to remember because we'll be seeing it again soon. Because if there's more than one planet in the system, the other planets will gravitationally perturb the planet we see transit, meaning outer planets which we cannot see will affect the orbit of the visible planet that does transit. When this happens, that mid-time gets shifted. So it gets a speed boost and it transits more quickly, then it misses the speed boost and it takes longer, et cetera, et cetera. Because of this, the transit becomes non-periodic, not in the same simple manner it was before. And you can see in this data here that it's shifting our mid-time back and forth over time. What's great about this and extremely useful about this is that this follows its own pattern. So I can trace a line all down this data going back and forth. It's still predictable. It's just not quite as simply predictable as it was with one planet. The variation in timing we see here, the back and forth, that sort of swing we see, is known as a transit timing variation, or a TTV. And this is specifically what I researched at Vassar. So here's a nice animation of what a TTV looks like, and I'll talk you through it as we're seeing it. So here's our basic transit setup. We've got our planet and we've got our star. And our planet is orbiting, often very close to the star, because again, we're often looking at hot Jupiters. So these are orbiting fast and they're orbiting hot. When it passes in front of the star, we get a mid-time, and it's always going to happen at the same time. Mid-time is now, and then it's going to pass behind the star. Mid-time happens again, and we pass back behind the star, just like clockwork, extremely predictable, extremely periodic, just like this forever. If, however, we have a more complex system, this transiting becomes more complex as well. So let's go ahead and add a second planet to our system and see how it affects my inner hot Jupiter. Well, as the hot Jupiter passes, it's going to get a gravitational assist, a little gravitational perturbance from my larger planet that's outside of my transit, which is going to cause a change in its orbit. So it gets boosted and it passes a little bit more quickly. Now there's no boost, so it takes longer. But then this time around, we're going to get boosted again. So a fast orbit, and finally a slow one. So fast, slow, as it's passing in time with the other planet. This is, as I said earlier, a predictable disturbance. We can measure this over time, and the more observations we take, the clearer that data becomes. This is something we can observe. This is an observational effect that not only can we observe with fancy space telescopes like Kepler, but we can observe with ground-based telescopes like the Vassar College telescope, which is just a 32-inch scope. This is the research I did at Vassar. Here is me with the telescope, and here are some examples of star fields that I looked at. To very quickly sort of run down the process of doing this research, what I did is chose several selected stars which we knew had transiting planets and seemed like good candidates for additional planets for many reasons. They were the kinds of stars that tend to harbor many planets, etc. When we take this data, I look at a star for a long night. Typically, these are stars that have proven transits, so I have a pretty good idea of when the transit will occur. The midpoint shifts, the mid-time shifts, are generally on the order of seconds to minutes, so it's not like I'm going to miss it by a few hours. Typically, we want to get about an hour and a half of standard observation before transit, hour and a half after. So you're looking at a nice night of observation, usually around 5 to 6 hours, depending on the star. What I'm doing during that time as an observer is choosing comparison stars that are known to be non-variable, as well as a check star, which is known to be non-variable, and keeping my star as centered as I can in the field while images are being taken. That data is then reduced. My target star, my exoplanet bearing star, is compared to the comparison stars, which I know are constant to make sure there's no atmospheric variations or other stuff going on. That data is then reduced and put into a transit curve, a light curve. From there, I'm able to determine what exactly is going on with that data and how the mid-time I calculate compares to the mid-time I observe. Here's some of my actual data from this project. So back here, you can see this is a WASP 80b, another one of the WASP stars, WASP 2b, gave me this beautiful light curve here. Here it is adjusted for the trend, and you can see the mid-time is noted there in red. The brightness is on the y-axis, so this is in magnitude, and the time is on the x-axis. What we're seeing on the y-axis is the change in magnitude typically. So how is the magnitude changing with the transit, typically measured in millimags. And then the time, of course, is measured in Julian date, as most astronomical observations are. The original data is here on top, the trend removed on the bottom. Basically, if something caused trending, usually something like atmospheric shifts, that is removed from the final data set. There again in red is the transit mid-time. This is the money. Like, this is a beautiful curve. We love that we can see a transit. What I'm really interested in with my data is the transit mid-time. When exactly did that planet cross? And is it when I predicted it to happen? After I have that information, I can craft an O minus C, or observed minus calculated, plot. Observed is what I measured. This is the actual thing from the actual data. Calculated is what it should be based off of a recently published time of transit. So essentially what I did there is I looked at the most recent published past transit I could find, and then took that data out to present time. All of this is going to have some error bar to it. There's inherent error in the calculation. There's inherent error in the number that was originally calculated itself. So you can see those sort of, let me pull up my little pointer. You can see that in our little lines here. The dotted black line is the exact calculated, but we have some error bars here. Anything within the green is pretty good. Anything within my other error bars is also going to be like probably okay, but less great. If we're outside my blue dotted lines, outside my different error bar measures, that's when we're starting to look at an effect that could be caused by a secondary planet and not just by error in the calculation because it was done so far in the past. You can see, I like comparing these side by side. The Qatar 1b data, this top plot, is from a star that is much dimmer because of that has a much more error-filled calculation of mid-time. So that's why my error bars are so dramatic. Whereas Trace 5b is much easier to calculate and has been calculated much more, and therefore is a little bit tighter on its error bars. So not quite as much error over time there. So the error compounds over time, and that allows us to see if what we're seeing is probably a real or unreal effect. Trace 5b is a very interesting case. You can see I took 4 observations of it over my about 5.5 months of observing when all was said and done. We've got 3 that are very close together and 1 that is dramatically not. In my paper, I expressed this as what we would expect to see if we were getting an actual variation in timing. This is an impossible thing to measure with 4 data points. You would want to look at this star for a year or 2 to get enough data to actually say if this is a real effect. I had 4 data points. I cannot make any claims about whether Trace 5b has a companion planet. All I can say is this is what it would look like. What's interesting is a few months after I published my data, Trace 5b was in a different paper stating that it probably had a companion planet using this method. So what I said was probably a real effect was later confirmed to be a real effect. So Trace 5b does have a companion planet, which is very cool. So here we can have here's an O minus C plot from a published paper. This is the O minus C plot of Kepler 19b, circa about 2017. And you can see here, there's that shift I was talking about earlier, how it's sort of in that periodic variation. Not as nicely periodic, of course, as like a single planet going around, but because orbits are predictable, our variation itself is periodic, which is quite lovely. This system, Kepler 19b, actually has 2 additional non-transiting planets. And again, this is data taken over a long time. This published paper had about 4 years of Kepler observations that were used to find these 2 additional planets. And there are some very famous systems found with transit timing variations. Perhaps the most famous is the TRAPPIST system that was found in 2016, which made news headlines and really sparked our imaginations around the world. The TRAPPIST system had 7 planets that were found, all very close to a very dim star, so very close to each other, but still within a habitable zone. About 3 of them were potentially habitable. When we look at the data, this is the TRAPPIST data, it looks kind of like data soup. It's really hard to see what's going on. So here on the bottom, you can kind of see where all of the variations are. That's my dotted dots here. And if we break those down, we start to see how my variations are planet dependent. Here's my first set of variations. Isolated, those look pretty darn periodic. We're seeing it over a set amount of time. Now we can isolate my next planet. Planet number 3, and so on. So breaking down this data, you can see that we are seeing 7 distinct planets that are causing perturbances that are periodic. Which begs the question, why does this matter for life? It's a very cool thing. It's a very cool use of data and math, and it's a cool way to apply math to observation. But what does it mean? Why is this something we can use to look for potential life? Well, let's start by thinking about what life as we know it really is about. You might be tempted to think, okay, food, water, shelter, that's what we need to live. But I'm thinking bigger picture. Don't think about the triangle of life. Let's think instead about the circle of life. Things like carbon, liquid water, sunlight, and oxygen. Things that every living thing on Earth needs to exist. All basic life forms need these 4 things. Oxygen is particularly necessary for complex life. So oxygen is one that we look for, particularly if we're thinking about intelligent beings. How we get these is where my TTVs come into play, because it turns out that it's very specialized to get all of these things together. In order to have these 4 things, planets must be around Earth-sized, orbit in the habitable zone of their star, and hold liquid water. If we can check off those 3 boxes, we can say that this is a potentially life-harboring planet. So first, let's talk about Earth-sized planets. Why does that matter? Well, to kind of get to the root of that, we need to talk about planetary formation. When you form planets, only Earth-sized planets can hold liquid water. Planetary formation, super quick crash course, you have a molecular cloud. The cloud collapses due to an outside disturbance, usually something like a gravitational wave or maybe an inside disturbance. Something happens that causes the cloud to collapse. It collapses, it forms a protostar, and around the protostar eventually forms a protoplanetary disk. The disk then eventually forms planets. When planets are formed inside this tumultuous system, larger planets retain gases they form and become gas giants. And super Earths, I mentioned those very briefly at the beginning, is probably a misnomer, and they're probably also gas giants. They're not sort of rocky planets as we think of them. When this happens, basically, the gas giants cannot hold liquid water because all they have is a sort of liquid metal core surrounded by gases and all kinds of crazy stuff going on. There's no place for liquid water to exist. This also begs an interesting question around hot Jupiters, which I could do a whole other talk on because the formation of hot Jupiters is a whole other thing. But essentially, in order to hold liquid water, you must be a rocky planet and you must have formed close in. Why the habitable zone? A habitable zone, also known as the Goldilocks zone, is the range of orbits around a star which can support life. This, of course, depends on the mass of the star. More massive, more brighter stars will have a habitable zone that is further away, and dimmer stars have a habitable zone that is closer. You'll notice that my K stars down there, my red stars, have a habitable zone with a 0.1 radius of orbit relative to Earth's, meaning you can be very, very close to a red star, to like a K star, and still have life. And this is what we see with TRAPPIST. The TRAPPIST planets orbit extraordinarily quickly, but are still life potential because they are around such a dim star. In our own solar system, Earth, of course, is in our habitable zone. This is where liquid water can exist and sunlight isn't so harsh that it causes massive greenhouse gas buildup on the planet. Mars and Venus are ever so slightly outside the habitable zone. Mars especially is like very close to the border. Mars being so small also doesn't help its habitability. Mars's smallness means it does not keep an atmosphere, meaning it's also not habitable in that way. But Mars and Venus, very close, not quite in the zone. Here's that with the TRAPPIST system. This is, I think, an incredibly cool graphic. You can see just how close these guys are, just to really point it out for you all. This inner circle in our solar system that is less than half the distance to Mercury is in the TRAPPIST system, an entire system of planets, of which 3 are inside our green habitable zone, TRAPPIST E, F, and G. So these are very close together, very close in, and moving very quickly. I like to think this is part of the reason that the public was so enamored by these planets when this research was published, because imagine you're that close to another planet. There's a really good chance that as soon as you become spacefaring, you can become interplanetary because you're just so darn close to your neighbors. So it's a very, very cool system. And finally, liquid water. The fascinating thing about liquid water is there are a lot of theories around how liquid water came to be on Earth, and we're not entirely sure which one is correct. This kind of stems from the problem that very warm temperatures and a non-existent atmosphere in the very early days of Earth means that any formed water probably would have evaporated before the planet could cool. So we also think that a possibility might be that water was originally delivered by comets and asteroids, migrating planets. This is the idea that water was brought here. This makes it very difficult to try and predict if a planet will eventually have liquid water on it, but that doesn't mean we can't look for existing liquid water. So now, how do we figure this stuff out? First of all, let's talk about size. How do we know if you're an Earth-sized planet? Well, with a transit, we have talked about how much the star is being dimmed, corresponding to how big the planet is. The period tells us how far the planet is, and from that we can deduce radius. So basically, how big are you? How far away are you? A little bit of geometry tells us how big you are intrinsically. So you can see here, my top planet is much smaller compared to the star. My bottom planet has a much bigger effect, and we can use that in the period to work backwards to size. With radial velocity, we can actually use the conservation of momentum. With many, many transits, we can occasionally use both transits and radial velocity, which can give us a nice wealth of information there. Which means with radial velocity, we can also find mass. So we can find radius with transit, we can find mass with radial velocity, meaning we can put those together and find density, which is what we're particularly interested in, looking for Earth-like planets. With a transit timing variation, we can infer the characteristics of a perturbing planet because the perturbation depends on mass. So we can work backwards to find the mass of a perturbing planet. This is one of my favorite quotes. It's about our own solar system. This is Arago on Urbain Le Verrier, who is the man who discovered Neptune. Quote, "He was the man who discovered Neptune with the point of his pen." So much in the same way, we can discover perturbers with the point of our telescope. And as I said, with both mass and radius, we can find a planet's density and therefore composition. This is kind of where the money is, right? Like if you have a Jupiter-sized planet with a Jupiter density, you're looking at things like molecular and metallic hydrogen. We're looking at an Earth-sized thing with an Earth density. We're looking at the crust mantle core model that we're so familiar with our own planet. Because of this, we can use mass and radius to infer whether the planet might be water sustaining if it is the right density to hold water, as we talked about before. How we look for existing water all boils down to transits and what transits really mean. So again, TRAPPIST planets are close enough to their star to support liquid water. James Webb Space Telescope is also able to detect the presence of liquid water on planets, and it does this using a spectrometer. When there is a lunar eclipse, the moon turns blood red. It does this because when the Earth is between the sun and the moon, the sun's light actually still shines through Earth's atmosphere and onto the moon. When the light shines through the atmosphere, Rayleigh scattering happens. And when Rayleigh scattering happens, we filter out all the blue light and all we're left with is red. That's the same effect we see with exoplanets. We're actually looking at light shining through their atmospheres into our spectrometers. Because of that, we can look for chemical traces of water in the planet's atmospheres. And you can see here a hydrogen atmosphere and a water vapor atmosphere have very, very different spectra. Spectral work is really cool. I actually did some spectral work with MIT a few years back, looking at Europa, one of Jupiter's moons. It's really, really cool stuff. And James Webb is going to be incredible for finding atmospheric effects of exoplanets. So here you can see some work that's actually been done on this. This is HAT P11b, which is a planet I've actually looked at myself. Here you can see the best fit model for our real data compared to a pure water model and a cloud-free model. So we're somewhere in between pure water and a cloudy model, suggesting that there might be some water on this planet. So at this point, I like to give a really big disclaimer, which I call the life as we know it disclaimer. As this disclaimer suggests, all of this is talking about the search for life that we recognize as life. This is the kind of stuff we can see. This is life that looks like the life that originates on Earth and ignores the very real possibility that other kinds of life might exist. There might be methane-based life, there might be gas giant cloud life. We don't know what it might look like. We can only look for what we know. So even though we're only searching for the kind of stuff we can see, we're doing a pretty darn good job. And I'm very firmly in the belief that eventually we will find something. So thank you all for listening. And at this point, I'm happy to take any questions you might have.
Yes, could you talk a little bit more about the perturbing planets? You mentioned one of the attributes you could determine. Could you talk a little bit more?
Yeah, so the perturbing planets in particular, all of the information we can get from those, we glean from the planet they are perturbing. So mass is primarily what we can see there. We can also get a sense, because we can get a sense of mass, of distance from the star. Because it's not transiting, we can sort of infer from there as well. And typically, these perturbers we have found have tended to be quite Earth-like primarily, because they are out enough that they're not transiting. So transits rely on being close to your star. And because their masses tend to be more in the Earth camp and less in the Jupiter camp. This also aligns with what we see in our own solar system in terms of having Earth-sized stuff at Earth distance. What's really fascinating about the systems we see with exoplanets is that they don't align with our own solar system model. We don't have hot Jupiters, which actually makes it quite challenging to draw comparisons between some of these systems and our own. But what we're seeing with perturbers tends to be Earth-like stuff, which makes it very useful for this life hunting work. Good question.
Yeah,
I think I saw a hand. Yeah.
Yeah, I wanted to my compliments on a talk that's been very well given and well organized.
Thank you.
Yeah. Now the planets you're detecting with this TTV, and some of them might actually be transiting themselves. If you could use the data, it seems to me, from your TTVs to predict where the transits could occur if they are actually in the right place, in the right, not transiting, if they're actually transiting. Have you ever done that and actually check to see where it would transit if it's if it's actually transiting?
Good question. So many of the TTVs we find tend to be very small. And because of that can be difficult to detect with transits, just because the brightness difference is so much smaller than when you have a hot Jupiter that close in. For example, a transit of Venus would be undetectable in a solar system that's not our own. It's just too small of an effect to register from that far out, if you're not seeing it visually the way we are. So because of that, a lot of those smaller planets either don't register as transits or simply too far out to transit at all.
Yeah, it's just that if you have enough data over long enough time, and I'm sure you've used this trick before where you fold it over for different frequencies, you can increase your signal to noise, and maybe you can detect a transit that way.
Right, like if you say, we know it's transiting at this, between this time and this time, can we just sort of stack those? I have never tried it, but that's a really interesting idea, for sure.
Yeah, you might want to try that, because if you could have a confirmation of what you're detecting, right? That might be interesting.
Right.
So,
yeah, and mathematically, absolutely, you would know when that transit is occurring.
Yeah, you just have to pull it over with the right period. So you try different periods, slightly different periods, and see if they overlap, and it might be worth trying. Yeah.
Absolutely. Yeah, thank you for the suggestion.
All right, thanks.
Yeah, Alex,
Get closer, Paul.
In recent years, I've read that people are starting to think that not only might we have exoplanets with life, but many of these planets might have moons where there might be life on the moon. Is it a problem that the moons are so small that we can't really detect them to figure out what their composition is?
That is a great question. So yeah, moons are really like an excellent candidate for life. And we see that in our own solar system. Jupiter's moons in particular are of huge interest. Some of Saturn's moons, like I mentioned, I did some work with MIT on Europa and looking for Europa's oceans. So moons are a fantastic candidate for lots of reasons. A lot of times you can have gravity from the planet causing some heat coming from the inside of the moon, which can be very helpful. But as you said, they're small. So exomoons are incredibly difficult to detect. I do think we have done it before. I'm going to put a little asterisk on that because that is just I believe I saw it somewhere. I think that we have seen evidence of exomoons, but doing the work of, for example, spectra, which is something we use primarily with in solar system moons, they're just too small to get like good spectral data from this far away. So moons in general are a great candidate for life, especially in our own solar system. Exomoons also would be just really challenging to actually get data from.
And one other quick question. Have you done anything with rogue planets?
Rogue planets. Oh, I love rogue planets. So I have not personally done anything with rogue planets. They are very difficult to detect and to hunt down. And I also like to, I'll just add, the planets that we're looking at are hot Jupiters, not because there is such a wealth of hot Jupiters, but because it's very specialized toward what we are able to see. So what we are able to detect as far as exoplanets goes is big stuff close to stars. We're only looking at systems that are sort of frisbee face on to us when we look at transits. So this is an observational effect, right? Like this is an observational bias we have is toward these very specific kinds of systems, because this is what our current technology can do. So rogue planets are awesome. My research we can't see them. So I haven't dealt with them because of that. But they do exist and they're very cool. So the observational bias has not tilted that way yet. Maybe one day.
Okay, I have a question for you, Alex. It's a two-parter.
Okay.
One has to do with your the observatory available to you that you're actually developing, and the other one has to do with the follow-on to the Kepler Observatory and what hopes you have for that. So let's start with the Meridian Academy Mobile Observatory, or MAMO. Am I saying that right?
MAMO, yes, the MAMO.
What do you have in mind?
Great question. So the MAMO is a recent creation of mine. We essentially have a nice mount and a nice 9.25 inch scope, a very, very excellent CMOS camera. So we have a pretty decent setup, and we've been able to see some variability of stars with that setup already. My hope is that that variability will allow us to observe at least very deep transiting exoplanets.
Sure.
Just because of weather reasons, like we started to be able to get photometry data in like late November. So we have not been able to come back out and confirm just because it is so darn cold out there. But my hope is that in the spring, we can start to hunt down some very deep transits. A lot of my work at Vassar really centered around best practices for recording these with a small ground-based telescope in particular. So I'm hopeful I can take some of those tips and just translate them straight across to the MAMO. These are things like taking flats every night that are very precise, into using the red filter for some planets and the blue filter for others, depending on their magnitudes and surrounding stars. Certain rules and guidelines for check stars and comp stars. So a lot of the actual thesis paper that I wrote also depended on observational best practices. So I'm hopeful I can sort of like do some translating of that into the MAMO, and sort of use those tips and tricks to help us get some good data. So stay tuned for about March when we'll figure that out.
And so you're going to be engaging your students with this, I'm sure.
Yes,
And,
that is the goal.
So my second question has to do with, now I remember, TESS, the follow-on to Kepler. I don't remember what it stands for, but I'm sure you're interested in the data that it's providing.
Yes. So I'm just gonna try and jog my memory also of what TESS stands for, because it is, yes, the Transiting Exoplanet Service. I knew it was transit in there somewhere. Transiting Exoplanet Survey Satellite. I am myself observationally biased, but I really do think that transits are one of our best bets for finding potentially life-supporting planets. We've found some that are potentially life-supporting, and that's because of the things I outlined, right? Like a lot of transiting planets also allow us to take radial velocity because they tend to be hot Jupiter-esque, very close, very big, and show us the radial velocity wobble, which means we can pull a lot of information. We can pull atmospheres, we can pull sizes, we can pull densities. So I think in general, focusing on transits is a great idea. And I believe, if I'm correct, TESS is covering an incredible area. Like I think it's covering like hundreds of times greater area than Kepler is.
Right.
So it's very exciting that research is still being done. It's very exciting that transits is the direction we're going. And I do think that we will be able to find some really great planetary candidates now that we're looking in such a huge chunk of the sky. We've already found thousands, right? Like how many are we going to find now with TESS? So it's a very, I'm very excited that this is sort of the direction astronomy is sort of leaning in.
All right. Thank you. So I'm going to bring up the gallery here and to see if there's any other questions by any of the folks. Mike Deneen, president of the Gloucester Area Astronomy Club. Do you have any thoughts? Unmute. Unmute. Unmute.
That was a lot of overhead to say, hey, I'm good. It was very complete and very well done. Bravo.
Thank you. Thank you.
All as a result of stumbling into you in the darkness in a
Love
parking
it.
lot
It's great.
next to your telescopic rig. All right. So we have
Can
a
I
question from Irene.
Yeah, thank you. First of all, thank you for having me as a guest, but I just want to say, Alexandra, Eleanor and I are both on the board of directors of the Astronomical Society of the Palm Beaches down here in Florida, and we're both blown away. We're so impressed with this presentation. We're wondering if you would make another one for our club. And could you put in your chat how you could be reached, how we could reach you? If
I would love to, absolutely.
this
I'll go ahead and give you my
I'd really appreciate it.
Meridian Academy email, which I check very often. Beautiful.
This is one of the best I've seen presentations, and I need to see it again for it all to sink in.
Thank you so much. I really appreciate it. Thank you.
Thanks
So
for the
Bill Wall
information.
has a question.
Oh, yes.
Yeah, Yeah, I mean, yeah, we get to see this again because there'll be a video, so that'll be useful too. So, yeah, I wanted to mention the pulsar planets because, well, they're either the first exoplanets found, or, well, depending on who you believe, among the first. I mean, the method used is it's not exactly the ones you've mentioned, but it's similar to the radial velocity method, except that the kind of Doppler shift was the timing of the pulsar rather than from spectra. So.
Yes, absolutely. Yeah. So the pulsar planets, I believe, are similarly perturbing the pulsar as we see it, and we saw the difference in the pulsar period, correct?
Yeah, that's
Great.
right.
Yeah. So exact same like math background for sure is like, how can we infer planetary features from perturbations? Absolutely.
Yeah, and the planets, there was more than one, so they're perturbing each other. So that was also inferred from the pulsar timing. So.
Absolutely.
All right.
Great.
So do we have any more questions for Alex? Or we're going to call it an evening? Okay, well, I am so grateful to you, Alex. I'm grateful for just the serendipity of stumbling into you.
Thank you for having me. I had a great time.
And I really wish you great luck with working with your students to do some of this authentic research.
Thank you so much. And thank you all for coming and for being here.
Okay, excellent. Take care.
Thank you.
So long.
Bye.